Welcome once again to data science class. Um, Remember, in the last class, we promised that we are going to um, start with symmetry. Symmetry. Um, we promised we are going to start with symmetry. We are going to start with symmetry. Let me zoom out a bit so that you can have a good view of what I'm doing. So we promised we are going to be starting out with symmetry. And well, just to assure you that I've not forgotten, this is symmetry. But we are going to not just have symmetry. We are going to quickly run through what symmetries are. I want symmetry is, what encompasses, or what symmetry comprises of, so that we can move to a well solved or a well calculated topic or concept called Bayesian inference. You understand? So, but before Bayesian inference, I just need to give explanation on symmetry. Symmetry. I won't do so much. I won't do much of calculations. I will just give an explanation. It's something that I should skip, but I feel no that I should, you know, let you know for knowledge sake. You understand? It's something that is keepable, but no, for the sake of knowledge and for the sake of something you can refer to in the nearest future or in your journey in your career journey, uh, I should say something or give an overview of it or give an explanation on what symmetry is, so that you won't get confused as to when we start touching Bayesian inference and stuff like that. You understand? Or when we start touching much more advanced concepts, so you won't get confused as to where terms are coming from and stuff like that. So, what is symmetry? Well, symmetry is just a fundamental concept, found in various domains, including mathematics. It can be found in mathematics, physics, arts, and nature, of course. So it refers to a balanced and harmonious arrangement of elements or properties that exhibit a pattern of similarity or say equivalence. You understand? It is in its simplest form, symmetry can be understood as a correspondence or reflection of one part or side of an object, um, image or system to another part or side. You understand? So when an object or system possesses symmetry, it means that certain transformations can be applied to it, such as rotations, translations, or reflections, without changing its overall appearance or properties. Symmetries can be classified into several types. Um, we have reflectional symmetry, reflectional. We have reflectional symmetry. We have reflectional symmetry. What is reflectional symmetry? It is also known as mirror symmetry. It occurs when an object can be divided into two equal halves, and each half is a mirror image or the other. You understand? You understand? So a good example is a butterfly or a human face. You understand? So that is reflectional symmetry. Another kind of symmetry, another way a symmetry can be classified, another type a symmetry can classify into is we have rotational symmetry. We have rotational symmetry. What is rotational symmetry? Rotational symmetry occurs when an object can be rotated by a certain angle around a central point, you know, and it looks the same in multiple positions. So let's say a regular polygon, polygon, five-sided or um, object. We have like a square or a circle, which exhibit what rotational symmetry. Another type of symmetry I can quickly think of now is I think we have translational. Yes, translational symmetry. Translational symmetry. Transitional symmetry. Transitional symmetry involves shifting or translating an object or pattern by a certain distance in a specific direction without changing its overall appearance. You know, it is often observed in repeating patterns such as styles or wallpaper designs. You understand? The other one is rotational reflectional symmetry. Yes, rotational. Let me see. Rotational reflectional symmetry. Another one is rotational reflectional symmetry. This type of symmetry combines both rotational and reflectional symmetry. It means that an object can be rotated and reflected simultaneously to produce the same appearance, like a snowflake. I don't know if you have seen a snowflake before in the movie. You know, this is Africa. I don't think we have such in Africa. So, but you would have seen a snowflake in uh, on the TV. You understand? So, snowflake often exhibit this type of rotational symmetry. Then that is that about symmetry. These are the four I can think of. So right now, major ones, anyways. So symmetry plays uh, a crucial role in our various disciplines, especially in data science. You know, in mathematics, data science, statistics, or whatever, it plays a major role. You understand? Whatever discipline, data analytics, and stuff. You know, in mathematics, symmetry is extensively studied in mathematics, particularly in the field of, for those that are coming from the mathematics background, like myself, in the field of group theory, which formalizes the concept of symmetry and its property. It has application in geometry, algebra, number theory, and other branch of mathematics for those that are coming from mathematics. And of course, in physics, symmetry is deeply connected to the law of physics. You know, the principle of symmetry uh, underline fundamental theories, you know, such as quantum mechanics and relativity. You know, we have conservation law, such as the conservation of energy and momentum, which arises from the symmetry of physical systems. You understand? So I think I'm getting to forget the physics that I've been taught in my secondary school. Anyways, that aside, so of course, symmetry also can also be also has finds relevance in art and design. You know, symmetry is a fundamental aesthetic principle in art and design. You know, artists often employ symmetrical arrangements to create balance, harmony, and visual uh, appeal in their compositions. You know, symmetry can be found in architecture, paintings, sculptures, and of course, various art forms. Then it can also find relevance in nature. You know, symmetry is prevalent in the natural world. You know, many organisms exhibit symmetrical body structure, such as bilateral symmetry in humans or radial symmetry in starfish. You know, yes, the natural pattern like the fractal branching of trees or the arrangement of petals in flowers often display what uh, symmetrical properties. So, overall, we can symmetry represent a fundamental principle of order and balance, and its presence can be observed in numerous aspects of our surroundings. You understand? So, it provides framework for understanding and appreciating the harmony and structure found uh, in the world around us. You understand? So, without having so much verbosity and jargons. I think we need to also understand the concept of symmetry of combinations, you know, because we need to go back from general to particular. And our concern here is what symmetry of what as it relates to what combination, symmetry of what combination. Now, symmetry of combinations. Symmetry of combinations, uh, let me say, in the context of mathematics, the symmetry of combinations refers to the symmetry exhibited by combinatorial objects or arrangements. You know, so combination involves or sorry, combinations involve selecting or arranging of a subset of an element or subset of elements from a given set without regard to their order. You know, the concept of symmetry in combination arises when certain arrangements or selection possess equivalent or indistinguishable properties. You understand? So let's consider a few examples. Let me think of few examples. We have examples. Let me say examples. Examples. We have one. We have combinations with identical objects. Combinations with identical objects. Uh, uh, when selecting on or arranging objects from a set that contains identical elements, the concept of symmetry arises. So, for instance, if you have a set of three identical red balls and you want to select two of them, so the combination is got to be will now be what? Red ball one, red ball two. You understand? And red ball two and what? Red ball one. Let's say, for example, let me repeat what I said. I said, for instance, if you have a set of three identical red balls, all three red balls, and you want to select two of them, the combination will now be what? Red ball one, red ball two, and what? Red ball two, red ball one. So, which are equivalent because the balls are what? Indistinguishable because they are all three red balls. So, in this case, there is symmetry in what? In the combination. So, another one we're going to be talking about is symmetry arrangement. Another example is what? Symmetry. Symmetry. Okay, symmetric. Let me not say symmetry. I think that's wrong. Symmetric arrangement. Arrangement. Symmetric arrangement. What is symmetric arrangement? Symmetry can also arise, say, in combinatorial arrangements. For example, if you are arranging a set of identical objects in a circle, the arrangement may exhibit rotational symmetry. So, if you rotate the arrangement by certain angle, it appears the same as the original arrangement. So the concept is commonly seen in circular seating arrangement or arrangement of objects on a circular table, like a round table, like we have in let's say for example, um, all these comedic show that or music show or any show that is a table of five, table of six, a round table of five, a round table of six, and all that. So I think the arrangement settings there will be what symmetric arrangement. So another one is symmetry in permutation. I think we need to do talk about that as well. Symmetry in permutation. Let me symmetry symmetry in permutation. Another one is what symmetry in what permutations. Of course, we all know that from our past lectures. We all know that permutations involve the arrangement of elements in specific order. So why not strictly combinations? Permutation can also exhibit symmetry. For example, if you have a set of distinct objects and you want to swap two objects in a permutation, so the new permutation may be considered symmetrical to the original one. So this is known as permutation symmetry or exchange symmetry. That's another word. So another word for permutation symmetry is what? Exchange symmetry. So symmetry in combination, from all this you will understand that symmetry in combination is not limited to this example, of course, and of course can manifest in various other ways depending on the specific context and constraints of the problem. You know, so recognizing and leveraging symmetry can often simplify the analysis and computational or computation of combinatorial problems by reducing the number of distinct cases to consider. So so You would agree with me that the study of symmetry in combinatorics is an active field within mathematics. So, with applications in various areas, such as, of course, like I said before, group theory, we have graph theory, and combinatorial optimization. So, understanding this concept of symmetries of combination can help in solving problems efficiently, and of course, uncovering, let's say, deeper insight into the structures and patterns inherent in combinational or combinatorial objects. You understand? So, uh, I think we've been able to uh, understand the concept of symmetry of combination. Please let me even summarize all I have said so that all those grammar or all those terminologies will be a bit simplified. Let me say picking more elements can lead to having fewer combinations, so generally we can pick p many elements in as many ways we can pick n minus p many elements. So we can apply symmetry to avoid calculating factorial of what large numbers, and we use symmetry to simplify calculations. So symmetry is very important. So we use permutation and variation when we are to arrange set of objects. So the order is also what crucial in permutations and what variations. So the difference between them is that eh, I'm trying to um, recall knowledge about permutations and variations here. So the difference between them is that in permutations, you always arrange the entire set of elements in a sample space. For example, let's say in a relay of say four runner, maybe of course if you have to arrange the winner in four positions, we use what permutations, because we have four runner and we are using all the sample space is four runner, and we are using the whole of sample space, arranging them. So but if you are to pick and arrange four winners and arrange in four positions from six runners, look at it. In the four runners and picking four runners and arranging four runners, you are exhausting the sample space. I told you the sample space is the total of everything there. So you are exhausting the what sample space. But in this case, where you have six sample space and you have four winners, and you want to arrange in four positions from what four runners, so we have what we use variation in this case. So alternatively, if you are to pick four winners from six runners, we use what combinations. You understand? But in combinations, you are not you are not in combinations you are not arranging. You are not no position. You understand? You are just to pick four runners. You are picking winners from six runners. We use combination. Order is irrelevant. You understand? But in variation, if you have six sample space, you want to find four winners and arrange them in what four position. But in permutation, you have six sample space of six. You want to arrange six. You understand? From that six, you want to exhaust, that is, you want to find six winners from what six sample space from six runners. You understand? So, or you want to arrange six winners in six position. Let's say six. You want to arrange six people in six position. You understand? In what six runners you get. So you're using permutation, you're exhausting the whole of sample space, but you're exhausting the whole of sample space. But in um in variation, I'm trying to repeat it. Out of six runners, which is the sample space, you want to arrange four winners to what four position, one to fourth. You understand? You use variation. But in combination, you are picking four, you are not arranging them. You understand? Combination does not care about order. So you have what six sample space, and you want to pick four winners, no arrangement. So that is that. So now this now brings us to the concept of Bayesian. I think I want to clean this off. So I want to talk about Bayesian, Bayesian inference, in Bayesian inference. And under Bayesian inference, we're going to be talking about set and we're going to be talking about set and event. We're going to be talking about set and event. You understand? So, other Bayesian inference, we're going to be talking about what? Um, we're going to be talking about set and what? Event. But before that, I think I need to explain what Bayesian is so that we can understand the concept. I like to come from explanation to solving to explaining again to repeating. You understand? I think that solidifies our um, learning and understanding. That's my belief. I don't know if you have a query against that. You can let me know, please. And if there's anything that sounds or that is looking hard, let me know so that we can schedule a one-on-one experience with each other. So we have Bayesian. Bayesian, of course, refers to the principle and method of Bayesian statistics, you know, which is a branch of statistics that deals with uncertainties and probability. When you have uncertainty and probability together. So it is named after this man called Thomas. It is named after Thomas Bayes. Sorry, Thomas Bayes. It is named after Thomas Bayes, which Thomas Bayes is I think 17 or 16, 17 or 18th century British mathematician and a theologian, of course, who developed the foundation of Bayesian inference. you know so at the core of Bayesian statistics, it has the idea of using probability to represent uncertainties. So unlike classical statistics, which treats probability as a long-term frequency, Bayesian Bayesian statistics interprets probability as a subjective degree of belief or plausibility. You understand? So plausibility, this is the spelling of plausibility that I just said. See, what's the spelling? P L. I'm trying to, for real. I'm forgetting the spelling. Um. Okay, I think yeah, plausibility. Yeah, this is the spelling of plausibility. So, it allows us to quantify and update our knowledge or beliefs about a particular event or hypothesis based on new evidence or data. You know, so the fundamental concept in Bayesian inference is the Bayes theorem. Bayes theorem. We have Bayes theorem. Bayes. We have the Bayes theorem or Bayes theorem, whichever case you want to call it, or whichever way you want to pronounce it. So the fundamental concept in Bayesian inference is the Bayes theorem, which mathematically describes how to update prior beliefs in light of new evidence. So this is how to state the Bayesian this thing. It has a formula. Let me just write out the formula. Uh, Let me write them out. We have, say, P. Please, my writing is bad here. I'm not using a real pen. P uh, H slash E is the same thing as P is equals to uh, P. We have E of H. We have E of H. Uh, Sorry, let me clean this off. PE of H times, times in mathematics is the same thing as asterisk. So, but let me use the proper times. Times, say, P uh, P of H. We have P of H. So excuse me. P of H. P of H. You understand? So we have P of H of E equals what? P of E of H times P of H divided by, say, P of E. So these things, what do they mean? What do these things mean? You see this one here, this one here, this one. It means it is the posterior probability of hypothesis H given that what? Given evidence E. It is the what? Posterior probability of hypothesis H given evidence E. You understand? Why this one here? This one here, this one here is the probability of observing evidence E, given that what? Hypothesis H is what? True. You see the difference? Don't get it confused. This one means the posterior probability of hypothesis H given that E, given evidence E. You understand? Then this one means the probability of observing evidence E given that what? Hypothesis H is what? True. And this represents it represents the likelihood of data under what? Under the hypothesis. Then P of H is what? The prior probability of hypothesis H, which represents our initial belief or knowledge about H before observing any evidence. And of course, P of E is the probability of observing evidence E. You understand? Which has as what? A kind of a normalization factor. So please don't get yourself confused as to that. So according to Bayesian's theory or Bayes theory, the posterior probability of hypothesis is proportional to the prior probability multiplied by the what? Likelihood of an evidence, which is this formula that I just gave you. So in other words, we can say we update our beliefs by combining prior knowledge with new evidence in a principled and coherent way. So Bayesian inference involves an iterative process of updating belief as new data becomes what? Available. So initially, we start with a prior belief, and as new evidence is observed, we compute the posterior probability. So the posterior becomes the prior for the next round of inference, and of course the process continues like that. So the strength of Bayesian inference lies in its ability to incorporate prior knowledge or subjective belief, which can be particularly useful when data is limited or noisy. You know, so it also allows for the quantification of uncertainties by providing a probability distribution over the parameters or hypotheses of interest. You know, so Bayesian methods find applications in various fields, including machine learning, uh, data analysis, you understand, decision making, and artificial intelligence. So you will see that it's a very important concept. So whichever of this field you want to master, either machine learning, data analysis, data analytics, decision making, artificial intelligence, and stuff. You understand? So they provide a powerful framework for reasoning under certain under uncertainty, and enable us to make more informed and rational decisions based on available evidence uh, based on available evidence. So you agree with me? To another set an event, you know that any set that can either uh, uh, be empty or have values in it. You understand? That is set. I'm trying to define set now. So set is any set that can either be empty or have values in it. So if it doesn't have a value, it is known as what? Empty set or null set. So let me clean this up because I'm going to be making use of this whiteboard here. So any set can either be empty or have values in it. So that is the definition of set. So if it doesn't have a value, a set is known as what? Empty set or null set. What is a non-empty set? Non-empty set. Let me uh, a non-empty set or non-empty set. What is a non-empty set? Non-empty set can be, these are sets that has no that is not empty. That's just the simple definition. So it can be finite or infinite, depending on the number of elements they have. You know, but let me it is let me define. Let me see a way to define non-empty set so that I won't be just. It won't be as if uh, um, let me say non-empty set. Um, Let me look for a way to define it. Okay. Mm, okay, let me quickly explain what non-empty set is. It's a kind of term we use to describe a set, you know, or collections or container that contains at least one element. You understand? That is, it must have an element, it must contain an element. So, in other words, a non-empty set is not devoid of any element, or it's not empty. Let me not use devoid here. It's not empty of any element. So, at least it has what? One member. You understand? So, the concept of non-empty set is used to differentiate between sets or collection that have um elements and those that are what? Empty, meaning they have no element. That is, those that are empty. You understand? So it's a way to specify that a particular set or container is empty of content or devoid of content, and it contains at least um, uh, one item. So it's not empty, at least one item is there. So for example, a non-empty set can be, say, um, I would prefer, okay, it can be said to be, say A equals quickly bracket. Let me this quickly bracket here. So that is curly braces. Two, three curly braces. In programming we call it quickly bracket. Okay, so this set contains three elements. You will see that this set contains what? Three elements. You understand? And it's considered what? Non-empty because it has what? Three member. But when you have, say, let me use this B equals empty quickly, or there's something I can't type it. Okay, when you have B equals this, or you have something like this. You have something like this. Say this. It is not theta. Let me do it well. Let me use a tiny pen. This is not theta. It's sorry, I'm not drawing perfect. Oh shit. Okay, just manage it. So when you have something like this, this set contains no element and is considered empty. Is either you have this, or you have this. Do you understand? So it's either you have an empty quickly, or you have that phi sign. So this set has no what? Element and is considered empty. So the term non-empty is often used in mathematical context when describing sets, but it can also be applied to other data structures or collections such as list, of course, array or databases. So it serves as a kind of concise and explicit way to convey the presence of elements within a set or container, emphasizing that it is not what? Lacking any this thing, any um any it's not lacking any content. You understand? So that is that about um non-empty set. Of course, remember I said something about uh non-empty set can be either finite or infinite. So what is, when they say something is finite, what does it mean? When they say a set is finite, Let me quickly explain that so that we won't waste much of our time. In mathematics, sets can be categorized as either finite or infinite based on the number of elements they contain. You know, finite sets. Let's say a finite set is a set that has a definite number of elements. You know, it has an ending, of course. You understand? Say, in other words, a set is finite if it contains a finite countable number of distinct number. For example, this A here is called this set A here is called what? If it's an example of a finite set because it contains three distinct elements. You can count it there that it's three elements. You understand? So when you say a set is when I say B equals, can as well say B equals orange. Let me use a lowercase. Orange, I can say B equals orange, uh, apple. I can as well say banana. You understand? It is also a finite set with what three distinct elements. Finite sets can be explicitly listed, you understand, by enumerating all their elements or by using set builder notation. You understand? So that is about finite set. Then infinite set in the other way, let me write it out. Infinite set, let me use uppercase. Infinite set. Infinite set, uh, an element set is a set. An infinite set is a set that contains an infinite number of elements. In contrast to finite set, what we have said about finite set, infinite set have infinite sets have an uncountable number of members. It is not possible to list or count all the elements of an infinite set. For example, you can say, for example, if I just say A equals 1, 2, 3, and now put a comma and put say something like dot dot dot. That is what an infinite set. You understand? That's an infinite set. It's an infinite set because it continues indefinitely without an endpoint. You understand? So let's say the set of an integers. The set of integers are what? Let's say minus infinity to plus infinity. That is the set of an integer. You can't know where minus starts from, and you don't know where you understand the positive ones. And you understand. So it's another example of what infinite set. Infinite set can have various sizes or cardinalities. You know, some infinite sets, such as the set of natural numbers, have countable infinity, meaning their elements can be put into one-to-one correspondence with the natural numbers. You know, other sets like the real numbers have an uncountable infinity and cannot what be enumerated in this way. You understand? So the concept of finite and infinite sets are fundamental in statistics or mathematics and have implications in various areas, including set theory, number theory, and analysis. So, understanding the property and behavior of finite and infinite sets is essential um, for studying their structures, relationship, and what properties. So, that being said, let's talk about part of the set. You know, part of the set. Part of a set, it is also important to know if an element is part of a set. Let me let me know. Part of a set. Or yeah, let's just say. So it is important to know uh, if an element is part of a set. To denote that we use something like this. That is so to denote an element is part of a set. We use this kind of we use something like this. We can say, let me clean this off, please. We can say x. We have this sign here that looks like a. You know, we are trying to check a member of a set. So what this means, this is an element. This is an element. This is an element, and of course, and this is what? Set. You understand? So this is an element and this is set. So what it means is that X is an element of the set A. This simply means X is an element of what? Set A. That's the meaning. So when you have something like this, when you have something like this, say when you have um, A and the E is backing, sorry, the E sign is backing X. When you have something like this, it's just like writing the reverse of what we wrote before, and we have X. You understand? You know, initially we had this. You understand? A. So we said here that X is what? Uh, is an element of the what? Set A. This is an element, and now we now have this. Instead of the E facing this way, the E is what? Backing this way. So it's like just like having a mirror image of this, having a mirror image, a symmetry of this, a reflectional symmetry of this. Yes. So it's just like having a mirror image of this. So we can say that this simply means A contains what? X element. Set A contains what? X element. You understand? So please get that straight. Please don't confuse yourself as to that. So now we're gonna be moving to not part of a set. Not part of a set. Let's quickly move to not part of a set, because this is indicating. So when you say an element is not part of a set, you are invariably saying, okay, now let me say I want to say X is not in A. To say X is not in A, you simply need to what? Cross this. By crossing it, it shows S is not in A. And by crossing this, it shows uh, A does not contain X. That is just the difference there. So we also need to know about the generalized statement about multiple elements. Generalized statement about multiple elements. So what is that? Let me clean this up and explain what that means. When you have something like this, when you have something like this in statistics or mathematics, when you have something like this, this simply means this means um, for all. In mathematics or statistics, it means for all or any. It means for all or any. So invariably, if I now write something like this, if I write something like this, if I write something like this, you are invariably saying for all x in A, for all x in A, for all x in A. You understand? We have for all or any. Then this we have for all x in A. You understand? This simply means for all x in A. You understand? This one simply means for all x in A. You understand? Because this simply means for. This is just mathematical jargon. So please let it stick, please. So note that uh, whenever you have a colon, it is incredibly useful when we want to make statements about a specific group of elements within a set. Say we have something like this, we can have something like this, we can have something like this. Let me clean this off. We can have something like that. So what we now have, for example, we can say for example, um, this column means such that. In It means such that. This column that you are seeing here, it means such that. in mathematics. So uh, we can say Vx, this our view, it has to be stricken. You can say Vx, you understand, and have something like this, and have this. What this simply means is that, okay, let me write it out. Is even. This simply means that for all x such that for all x in A, such that x is what? Even. For all x in A, such that x is what? Even. This is what it means. So please, we need to be understanding this thing. If it means you have to, repeatedly listen to it, please, it's very important. It's very, very important. So then another thing we're going to be talking about is the subset subset. I quickly want to finish up with sets, and so that we can start doing calculations and stuff. So subset means it's a set that fully contained, or that is fully contained in another set. It is denoted as this. This is how to denote it. It is when a set is fully contained in another set, a subset. When a set is what? Contained in another set. For example, a pregnant woman, the baby inside the womb is a subset of that pregnant woman. You understand? That is the baby contained in what? In the uh, in the woman. You understand? So the baby is a subset of a pregnant woman. The baby inside the womb is a subset of a pregnant woman. I think that is the best example I can give right now. So note that this is how to denote subset. It means A is contained in B. So note that every set contains at least two subsets by default. You know, every set contains at least two subsets by default. A, when we have A, you understand, we have set of A. Definitely, A is a subset of itself. Note that first. One, that is the one. You understand? Because in the statement I just made said every set contains at least two subsets by default. One, a set is a subset of itself. And of course, an empty set is what? Is also what? A subset of a set. You understand? An empty set is also what? A subset of a set. You understand? A is a subset of B. Fine. That is, you are saying A is contained in B. You understand? Then I now said, note that by default, every set contains at least two subsets by default. Every set. A set, a set is a subset of itself, which is, I used A. So a set is a subset of A. And an empty set is also what? A subset of what? A set, of any set. So intersection. Now we're gonna be going into intersection, and let me clean this. We're gonna be going into intersection and union of union of set. Intersection. Let me spell it properly. Intersection. Intersection and unions, like union boys now, union, like union association now, and unions. So intersection and union. So let me first of all talk about what intersection is. Intersection means is set when it's set. Okay, let's say it is the outcomes that are favorable to both A and B. Intersection embraces a kind of conjunction and, you understand, combination, like the conjunction and, you understand. So it's an outcome that are favorable for both A and B simultaneously. So it means um when a set contain a when a set A contain an element that a set B also what contains together simultaneously. So it involves an element that uniquely common to both set A and B. So it is denoted by what? It is denoted by, say, A intersection B. You understand? It is denoted by A intersection B, which means A and what? B, which means A and B. The word and is important there, and B, which means A and B. You understand? So, um, this is how it is denoted. The another one is union. Let me talk about this union. Union, it's a combination of all outcomes preferred for either A or B. Union uses or, intersection uses and. You understand? So it is denoted as what? A union B. It is denoted as A union B. You understand? So you can say uh, so now, if you're in a set, if the set A, let's say we have two sets A and B, and if they do not touch in the inside the Venn diagram, if this is what the Venn diagram is, please. This is a Venn diagram where we have, sorry, my drawing is bad. When we have a set A and a set B. So if they don't touch, their union would be what? Set A, let me say set A and B. You will see that there is no intersection. When they touch, that is when there is intersection. You understand? So to find their union, it will now be what? A plus B. You will see that if they are not intersecting, it means there is no common element between A and B. So here we can now simply say, we can simply say from this Venn diagram, we can say A intersection B is what? Equals empty. Empty equals what? Empty element. And A union B is what? Because they are not touching, it will now be what? A plus B. It will now be what? A plus B. So when you are say um uh, uh intersect is what, okay, if the union intersect, we will have, okay, let's say if you are looking for uh uh we can equally say, if an intersect is given, maybe you have two elements, you have this, say two, you have this three, and you have intersect. They now say the intersect is what? Say they now give a question, actually given an intersect four and the union two, I mean, and given a set A having two elements and set B having three elements, and an intersection, find the union if it happens that the sets are not touching. You understand? So invariably, to find the union will now be what? You know, union, because they are not touching, it is A plus B. So to find the union when they are not touching simply means A, let's say A union B equals what? A plus B uh, minus A intersection B, because they are not what? Touching. So we can now say 2 plus 3 minus 4. 4 is a intersection. I think you're clear on that. Please, if you are still confused, please let me know. So conclusively, A union B is what? A plus B uh, minus A intersection B. So another important concept of set we need to look into is mutually exclusive. When they say something are mutually what? Exclusive. You understand? And I've talked about complement. You understand? So mutually exclusive. I think I would need you to, I would not want to give you so much of it until we move to the next class, where we'll be talking about mutual exclusiveness of a set. We'll be talking about a set is what? Mutually exclusive. Let me use uppercase. Mutually exclusive. You understand? And that will be your class for tomorrow. Please, thank you very much for your time. God bless. I want to appreciate every one of you for making up with making yourself available for this class. And so far, so good. We've been trying our best to make sure, or to making sure that we simplify every bit of what I'm teaching you. I've been trying to simplify them. And if you are still finding it difficult to understand every integrity or everything about what I'm doing, please call my attention to it and let me know. You can, of course, um, write a comment in the comment section. Write to me on Discord, write to me on Telegram. You can also write to me on WhatsApp or whatever. So that I can adjust and make it a bit fun than the way it is. And you can feel free to share it on YouTube. It's available for you are not restricted from sharing it. Of course, it's free. Feel free to share it. Of course, like our channel, you can you can like the video, click the like, and of course, give us a good comment, and subscribe if you think we deem it fit. Thank you very much um, for your support so far. Thank you, appreciate you, and of course, like I always say, please don't always make sure you write, you take notes. Of course, let's take notes. So we want to be fast as possible, so that we can cover up. And of course, after 3 months we go to our various we do all of the some of our any other thing that is needed to be done. Thank you very much, and God bless.